Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. In today's lecture, we will be seeing classification of rectifiers, input performance parameters. Firstly, what are rectifiers? It is a static power electronic circuit which converts fixed AC signal to pulsating DC output. See, if we are having certain AC supply and if our requirement is DC output, our requirement of load is DC output, in that case, we need a rectifier circuit which converts AC to DC. That is pulsating DC. It doesn't give pure DC. See, here we have certain input of sinusoidal nature, which is alternating. It has got both positive half cycle as well as negative half cycle. And if we need to convert this particular AC input to DC output, in that case, we need a rectifier which converts AC input to DC output. That will be usually, as I told you, it will be pulsating in nature. It will not be this pure DC, which is a straight line. And in order to obtain this pure DC, that is a straight line, in that case, we need to make use of filter circuits. We need to invest in filter circuits and in addition, some regulator circuits in order to obtain this constant DC output, and which is not possible just by making use of a rectifier circuit, which converts fixed AC to pulsating DC. After having investing in filters as well as regulators, we obtain this straight line. Let us see the classification of rectifiers. What are the types of rectifiers we have? These rectifier circuits are classified into uncontrolled rectifiers as well as controlled rectifiers. That is uncontrolled rectifiers as well as fully controlled. That is, we can also call it as phase controlled rectifiers. That is uncontrolled rectifiers. These are further classified into single phase as well as three phase type. Under single phase uncontrolled rectifiers, we have half wave rectifier, as well as we have a full wave rectifier. And if you consider three phase rectifiers are further classified into three phase half wave rectifier and three phase full wave rectifier. And these full wave rectifiers are further classified into midpoint type and bridge connection. Again, these three-phase full wave rectifiers are also further classified into midpoint type as well as bridge connection. Uncontrolled rectifiers are nothing but diode rectifiers. We make use of diode in these circuits. So that is the reason we cannot control the output voltage which is actually fed to load. We just can convert AC to DC. And coming to the phase controlled rectifiers, or we can also call it as fully controlled rectifiers. And these are further classified into single phase rectifiers as well as three phase. And here under single phase we have first classification is half wave controlled rectifier. Similarly, we have full wave single phase full wave controlled rectifier, and this full wave controlled rectifier is further classified into midpoint type as well as bridge connection. Similarly, in this full three-phase type, we have three-phase half controlled rectifier, half controlled, that is half wave controlled rectifier. Similarly, three-phase full wave, or we can also call it as fully controlled rectifiers. And these fully controlled rectifiers are further classified into midpoint connection and bridge connection. And in addition to that of uncontrolled rectifiers, in phase controlled rectifiers, we have single phase semi converter, or we can also call it as single phase semi converter, we can also call it as single phase half wave controlled rectifier, half controlled rectifier, single phase half controlled rectifier. And we also have, in addition to single phase semi converter, we have dial converter, single phase dial converter. Whereas here in fully controlled rectifiers, we also have three phase semi converter. This three phase semi converter, we can also call it as three phase half controlled converter, half controlled converter, or we can also call it as a rectifier. And we also have three phase dual converter, So in addition to uncontrolled type and a phase controlled type, we have semi converters as well as dual converter in addition. So here in output parameters, firstly performance parameters. In order to analyze any in order to analyze the output and in order to obtain best kind, in order to opt the best option, we need to compare all the output as well as input parameters. In that case, we can opt the best option. So that is the reason here we have some of the parameters which we need to compare in order to obtain the best option. And here we have firstly we'll see the output performance parameters, under which we have average output voltage. And average output voltage, in order to obtain this, here I'm considering a signal which consists of output from 0 to pi as well as from pi to 2 pi. And if you see, this is the axis with respect to omega t. And here average output, it is given by the formula V0 average. We can also call it as VL, we can load voltage, or otherwise we can also write it like this, that is DC output voltage. And here the general formula, in order to obtain any V output, average output voltage, V0 average is equal to, it is given by the formula 1 by T, 0 to T, V0 of dt. And here I am taking replacing time period is equal to replacing time period t is equal to omega t. I am taking this time period as omega t axis. In that case, if at all, if I differentiate it with respect to t, in that case we get 1 is equal to omega, and here 1 is equal to omega is equal to, we all know it is 2 pi f, In that case, if we take this f this side, 1 by f is equal to, it becomes 2 pi, and where we know 1 by frequency is nothing but time period, t is equal to 2 pi, and let me substitute this. Let me name this as equation 2 and this is equation 1. And now substituting time period in equation 1, we get the equation 1 transforms into V naught average is equal to 1 by 2 pi conducting from 0 to 2 pi V naught d, where t is equal to substituting omega t. And this is the formula in order to obtain the average output voltage. See, for this particular waveform, if at all, if we need to obtain the average voltage, in that case, we need to sum up the values at each point, is it not? And which is nothing but integration. So that is the reason here we are taking 0 to t, 1 by t. So this is the average output voltage. Similarly, in order to obtain the RMS output voltage for the same waveform, in that case, we need to write, we have a formula, that is V naught RMS is equal to, the general formula is 1 by t, 0 to t, V naught square of d omega t. V naught square d omega t whole to the power of 1 by 2. And in the previous case, for average output voltage, we have obtained the limits, that is time period is equal to 2 pi, substituting the same 1 by t. 1 by t is equal to 2 pi, 0 to 2 pi, V naught square d omega t whole to the power of 1 by 2. And this is the formula in order to obtain V naught RMS in a particular waveform. And similarly, we need to obtain the formula for form factor, where form factor, it is given by the formula RMS value, ratio of RMS value to that of average value. Since previously we have obtained V naught RMS as well as V average, we can write like this: V naught RMS by V average gives you form factor. Or otherwise, we can also obtain form factor using the current values, that is I naught RMS by I average. But mostly we will prefer voltage values itself. So this is the formula for obtaining form factor. And then we have a ripple factor. Ripple factor, it is given by the formula form factor square minus 1 under root form factor square minus 1. This is the formula in order to obtain the ripple factor. And usually ripple factor, it must be low. If the ripples in the circuit in the waveform is less, in that case the smoother the output DC waveform. So that is the reason we will see such that the ripple factor will be very less. And usually theoretically, ideally we can say ripple factor should be 0 and form factor usually will be 1 ideally. In that case, if I substitute form factor is equal to 1, 1 square minus 1 is equal to 0. So that is how it should be. And usually the ripples in the circuit should be low. That is the only reason they say ripple factor must be less. And coming to the rectification efficiency. So here rectification efficiency, it is given by the formula output DC power by output AC power. V naught I naught by V naught RMS into I naught RMS. This is the formula in order to obtain the rectification efficiency. And then transformer utilization factor. Transformer utilization factor, it is given by the formula output DC power. Output DC power by input secondary volt ampere. That is V0 I0 divided by input secondary volt amperes, in the sense Vs into Is. This is the formula in order to obtain transformer utilization. And then we have a ripple frequency. Ripple frequency, it is given by number of pulses per cycle multiplied by frequency. Number of pulses per the cycle, in the sense it can, in a cycle the number of pulses can be 2, 1. So that is the reason number of pulses per cycle is given by N and frequency is given by F. So ripple frequency is given by N multiplied by F. And in my next lecture, I'll be teaching input performance parameters. Thank you.